If we have a fixed number of independent trials, like 100, and I tell you we had 60 successes, then you're going to say, okay, we had 40 failures. With a fixed number of trials, if you know the number of successes, you know the number of failures exactly. They're a function of each other. But now we randomize the number of trials. So we're starting with a Poisson number of IID Bernoulli trials, and we've looked at the number of successes, and we know that that has a Poisson distribution. We're now going to look at the relation between the number of successes and the number of failures. Keep in mind that if I tell you that there are 60 successes and the number of trials is random, then you don't completely know the number of failures. So there is an interesting question about what is the nature of the dependence between successes and failures if you randomize. And it turns out that if you randomize appropriately, as we have done now, something remarkable happens. So let's note down what we know. We have a Poisson number of trials. We're running that number of IID Bernoulli P trials. The number of successes we've denoted capital S. Correspondingly, I'll denote the number of failures by capital F. And we found the distribution of S. So S is also Poisson. Not Poisson mu, but a proportion P of mu. Correspondingly, analogously, however you want to say it, F is what? Well, it's Poisson mu times Q. For our usual notation, Q is 1 minus P. Just change the definition of success and failures and apply our old result. Terrific. So we know the unconditional distributions of S and F, and we also know that if we are given the number of trials, so there's nothing random about it anymore, S, the number of successes, is then our old friend, the binomial. Because the binomial starts with a fixed number of IID trials. We're going to find the joint distribution of S and F. For this, what are the possible values? S is non-negative and F is non-negative. They're both capital S and capital F are Poisson random variables. We have to find the joint probability that there are little s successes and little f failures. Right, we don't actually know how successes and failures are related here. What we do know is how trials and successes are related. So let us rewrite this event in terms of the trials and the successes and failures. So if you have S successes and F failures, implicitly that's telling you the number of trials. You had to have had S plus F trials. Of course, you still want to force S successes. Now, I don't actually need to now say that we have little f failures because that's been included in the number of trials, that information. And this is good because by our usual multiplication rule, we have so you know that n is Poisson, and you know that given the value of capital N, the number of successes is binomial. So we just plug those two things in. All right, given that there were S plus F trials, what's the chance of S successes? Well, that's a binomial formula. Trials factorial divided by successes factorial, failures factorial, chance of success to the power number of successes, chance of failure to the power number of failures. Okay, so what happens? This cancels. And now I'm seeing stuff that has to do with S factorial and S factorial. And I like that because capital S is Poisson and as is capital F. So let's try and separate out. I'm going to try and rewrite this with some spaces. So I have an S factorial and an F factorial in the denominator. I'm going to look at what I have in the numerator and maybe collect some terms. So I have a mu to the power S here, and I have a p to the power S here. So mu to the power S times p to the power S is mu p to the power S. And so also we have mu to the power F and q to the power F. And so we have mu q to the power F, and the only thing that is left now is this factor of e to the minus mu. And what do you want to do with that? Well, look, you've got mu p to the power S over S factorial. You're seeing the Poisson distribution of S there, apart from the constant. Here you have mu q to the power F over F factorial. You're seeing the Poisson distribution of capital F, apart from the constant. Well, let's just put in the constants and see if we get into trouble. So this constant ought to be e to the minus mu q, and this constant ought to be e to the minus mu p. Now, what we have instead is e to the minus mu. And what we should have is e to the minus mu p times e to the minus mu q. What do you think? Yes, exactly. They're exactly the same. Mu is equal to mu p plus mu q because p plus q is 1. And so we have split, we have factored the joint probability that we have little s successes and little f failures into the probability that we have little s successes times the probability that we have little f failures. There's no conditioning there. In other words, what we've shown is that these two random variables are independent. The number of successes is independent of the number of failures. If I tell you in this situation that there were 60 successes, you cannot tell me anything more about the number of failures than you knew already, which is that it's a Poisson random variable with parameter mu q. That's a remarkable thing. If you have a fixed number of trials and I tell you the number of successes, you can tell me the number of failures exactly. That's as dependent as it gets. If you have a Poisson number of trials and I tell you the number of successes, well, the number of failures is independent. You know, see what happened when you randomize the parameter. It had a drastic effect on dependence and independence. Now, the fact that you get independence actually depends on randomizing with a Poisson number of trials, not with any other distribution. If you had any other distribution, you'd have got some different kind of dependence. But to get independence, you do have to start with a Poisson number of trials. So in summary, when you Poissonize the binomial, then the number of successes is Poisson, the number of failures is Poisson, and the successes and failures are independent of each other. This is extremely helpful for calculation.